Good morning again. We are going to get started. So we're starting with just a question that will get your brain going to be thinking about those mole ratios again. We've got this decomposition reaction, and you have to calculate the number of moles of oxygen gas produced from 5 moles of hydrogen peroxide. That means that you have to write a mole ratio. We're looking at these two compounds from the chemical equation. For our mole ratios, you write the numbers that you see in front of each compound as moles. So 2H2O2 would be written as 2 moles of hydrogen peroxide. And you write these like fractions. There's no number in front of the oxygen gas, which means it's 1. And there's 1 mole ratio. The other mole ratio is the reciprocal. Then we set up the problem. So our question we're trying to figure out how many moles of oxygen gas. Since we're trying to get rid of moles of hydrogen peroxide, we need to have that in the bottom of our mole ratio. So you should get 2.5 moles of oxygen gas. So that was just a little refresher, hopefully. How do we do on this one? If you didn't get a chance to do it, does it kind of ring a bell like, oh yeah, I remember that now, kind of, sort of? Okay. All right. So now we're about to get into the second part of Chapter 9. We're going to do a recap of the 2 problem types that we did last week. For the recaps, feel free to move ahead of me and work out the problem on your own if you feel comfortable doing that. The recap is really to kind of make sure that you got it. So I encourage you to try it out on your own. If you're still kind of shaky on it, it's fine. You can just stick with me and watch along. Then we're going to move on to a new problem type, and we'll introduce another couple of new concepts, and that'll be it for today. First problem type that we're going to recap is mass to mass. So that's when you have the mass of one compound and you're trying to figure out what mass of an unknown. So here we have what is the mass of zinc oxide that can be prepared from 1 gram of zinc metal. So those are the 2 things that we're interested in. Zinc oxide and zinc metal. I've got 1 gram of zinc metal, and I have to figure out the mass, which is grams, of zinc oxide. I've got a mass on both sides. I've got a mass of zinc. I need to figure out the mass of zinc oxide. So this is a mass-to-mass problem. Don't forget to do that when you're doing these problems on your own. Figure out which type of problem you have first, and that will help you remember how to do it. Or you can look back at your notes and know how to do it. I'll give you the generic way that we solved these last time. When you have grams of A, first thing you're going to do is convert to moles. And that requires the molar mass of A. In this case, our A is the zinc. It's the one that we have information about. Next, we convert that to moles of B. B is our unknown. So in this case, that's the zinc oxide, the one we're trying to figure out how many grams of it we're going to make. To get there, we need a mole-mole ratio. And it's going to be in the form of B over A. And that always comes from the chemical equation. And that equation must be balanced. From there, we need to get to grams of B. For that, we need a molar mass as well. We need the molar mass of B. Now let's write this with our specific compounds. We're starting with grams of zinc. We need to get to moles of zinc. The molar mass you get from the periodic table. Since we're just looking at zinc, you just look at the periodic table, see what it says. 65.38 grams. Okay. Then we've got to get to moles of zinc oxide. For that, we need our mole ratio. It's going to be in the form of B over A, so that means the number of moles of zinc oxide over the number of moles of zinc. And again, that comes from the chemical equation. The last step is getting to grams of zinc oxide, and that requires the molar mass of zinc oxide. You look at zinc, you look at oxygen, you add them together. Now it's time to put in the actual numbers from the problem. We're starting with 1 gram of zinc. We need to write a unit factor with the molar mass of zinc to get from grams to moles. Moles of zinc in the top, grams in the bottom. That'll get us there. Then we have to write that mole ratio, and it's going to have the moles of zinc oxide on the top. That's here. So we write 2 moles of zinc oxide and moles of zinc on the bottom. Last but not least, we need another unit factor that deals with the molar mass of zinc oxide. This time we're putting the grams in the top and 1 mole of zinc oxide on the bottom. Then make sure that your units cancel. And you can use your plan to make sure that they cancel in the right way. So we get to moles of zinc. moles of zinc oxide, and then grams of zinc oxide. To put this into your calculator, two divided by 2, that's 1. So you don't really need to put that into your calculator this time. And when you do that math, you should get 1.24 grams of zinc oxide. So that's mass to mass. Questions, comments, concerns? Did we try it at all? How did we do? All of the things. Let me know. So I have practice problems for you guys that I will post in Blackboard so that you can try this. And I'll put the answer sheet up as well so you can have something to try. And if you're interested, remember I have office hours today from 11:30 to 1. So if you want to do a couple of practice problems with me, come on through and we can do that together. Now we're going to do a recap of mass to volume. So again, feel free to try it on your own. I encourage you to do so. What is the volume of oxygen gas needed to fully react with 1 gram of zinc metal at STP? Anytime we see something at STP, we automatically assume there's going to be something to do with a gas, which means volume. In this case, we're starting with 1 gram of zinc, the zinc metal again. And we have to figure out what volume of oxygen gas we need to fully react with it. This is a mass to volume question. We've got a mass on one side and a volume on the other. So that's mass to volume. I'll show you how to do the kind of generic thing again, just to remind you. We're again starting with grams of A, which is what we're given in the problem. The first step is always getting to moles. No matter what you're starting with, you need moles. The zinc is our A in this problem again. You need the molar mass of A to get to moles of A. To get to moles of B, same thing, mole ratio. B over A. The oxygen gas is our B. The B is the unknown value, right? So whatever compound is associated with that, that's the B. Then we have to get to liters, or some kind of volume. Could be milliliters. And for that, we use molar volume. And that's only because we're at STP. One mole of gas has a volume of 22.4 liters. The unit factor that we use for this one is 22.4 liters for every 1 mole of gas. And you'll see that when I put the whole thing together at the end. Time to make it a little more specific for our problem. We said A is zinc, so we're going from grams of zinc to moles of zinc. So that first step is going to look exactly the same as the last problem. Then we get to moles of oxygen gas, which is our B. The mole ratio is going to be B over A, and it comes from the chemical equation. So the B is oxygen gas, A is zinc. Then we use molar mass to get to, or molar volume, to get to liters of oxygen gas. Now we fill in the numbers. This first part, we're writing a unit factor with the molar mass of zinc. We need to get to moles of zinc, so we put 1 mole of zinc at the top and then grams on the bottom. We already know what our mole ratio needs to be in this next one. It has to be the oxygen gas over the zinc, and we're getting our information from the chemical equation. There's only 1 mole of oxygen gas here, and that's what goes at the top. 2 moles of zinc. That's our mole ratio. Then we use molar volume to get from moles of oxygen to liters, the volume. Make sure that your units cancel. So we get moles of zinc moles of oxygen gas liters of oxygen gas. When you're putting this one into your calculator, you need to be careful. Parentheses are your friends. Use them. And when you do all that math, you should get 0.171 liters of oxygen gas. So talk to me about this one. Does it ring a bell? Or are you just like, oh man, we doing this again? The answer to that one, unfortunately for you, is yes. Okay. So practice, practice, practice. Practice makes better. I'm not going to say perfect, but it certainly makes better. And the more practice you do, the more better you get. All right. And yes, I said more better. I know what I said. So that's the recap. This is where we left off last week. We had done a volume to mass example, which is just the reverse of what we just did. You're starting with a volume of gas, and you have to convert that into grams of another compound. So I encourage you to try this one too. I'll talk you through it. I'll put up the generic plan again. But see how far you get. So yes, you could just divide by 2 for the last one. All right. So this problem, we've got how many grams of sodium chloride are produced when 9.21 liters of oxygen gas is produced at STP. So we know how much gas we made. We're trying to figure out how much salt did we make too. I'll give you the generic. This time, we're starting with liters of A. And A could be, it could also be milliliters, but a volume is what we're starting with. We're using molar volume to get to moles. So our A in this case is the oxygen gas. Then we have to use a mole ratio to get to moles of B. It's always in the form factor of B over A. And the one that you don't know information about, that's your B. Then we use the molar mass of B to get to grams of B. So I'm trying to keep the colors similar. So molar volume you'll see is purple. The mole ratio you'll see is green. Trying to keep the molar mass blue for B. I think all those things help when it comes to getting these problems down. So let's make this more specific. Our A is oxygen gas. So we're going to use molar volume here. Then to get to moles of sodium chloride, we need to use our mole ratio of B over A. So that's sodium chloride over oxygen gas. To get to grams, you need the molar mass of sodium chloride. And that equals 58.443 grams. Now, usually you will have to calculate that. But because we're trying to do class time and I just want you to understand the concept of how to get from point A to point B. I'm including the molar mass so that it's one less thing for you to do. But you'll need to know that for yourself from Chapter 8. I'm going to pause here and give you a couple of minutes to try to fill in your own equation in your notebook. So try to fill in the numbers just like I normally do, and see what you get. If you'd like to share your answer, you can. Don't feel pressured to, but I'll give you about 2 minutes to try it for yourself. I'm going to start filling in some numbers here. I'll fill in some numbers, and then we'll see. We're starting with 9.21 liters of oxygen gas. We're using molar volume, but this time we're trying to get to moles. So we need to have 1 mole on top and 22.4 liters on the bottom. And that's always what it's going to be when it's volume to mass. Then we need to write our mole ratio. It's B over A, so we need to look at the equation for sodium chloride, which is our B. We write that as 2 moles over the A, which is oxygen gas. Look at the equation, that's 3 moles. Then we fill in the molar mass. We want the grams in the top and moles on the bottom. Double check, make sure that your units cancel. So all that checks out. To put this into your calculator, you start with the 9.21, divide by 22.4, then you've got the 2 divided by 3, that's our mole ratio. And then the number of grams in 1 mole of sodium chloride. When you do all of that, you should get 16 grams. So if you didn't get that, hopefully you see where you went wrong. And if you want some help diagnosing that, again, office hours. Questions here? I know it's early to be doing all this math, but hopefully some of it is sinking in. So we've done mass to mass. We've done mass to volume. Now we're going to do the easiest problem type, which is volume to volume. This is for gases only. So it's much easier. I'll run through a quick example just to show you. How many liters of oxygen react with 37.5 liters of sulfur dioxide in the production of sulfur trioxide gas? We're starting with 37.5 liters of sulfur dioxide, figuring out how many liters of oxygen. We've got a volume on both sides. We're starting with the volume. We're asked for a volume. So it's a volume to volume question. When we're writing our mole ratios and we're only looking at gases, if we're told that we're at STP or that all of the gases are at the same temperature and pressure, then we can do this problem without having to do anything except use liters instead of moles in our ratio. These are the two compounds we're interested in. So I can say 2 liters of sulfur dioxide for every 1 liter of oxygen gas, and I can write the reciprocal. Here's my starting information. If I'm trying to go from the SO2 to oxygen, which one of these factors will I use, A or B? So to put that one into your calculator, you just take the 37.5 and divide by 2. And because of sig figs, when you round, I'll write it out for you. And that's it. That's volume to volume. We can write our mole ratios with volume instead of moles. And that's all you need to use. Questions here? Let me know if you're ready to try your own. So we'll stick with the same chemical equation. How many liters of sulfur trioxide gas are produced from 37.5 liters of sulfur dioxide gas? So that's your problem. You're starting with 37.5 liters of SO2. You need to figure out how many liters of SO3 you make. I'll give you approximately 2 minutes or so to get started, and then I'll check back in. Okay, so hopefully you had a chance to at least get started. We'll look at the problem and write out our mole ratios. These are the two compounds that we are interested in. We write the number that we see in front as a volume in liters instead of moles, and that's only for volume to volume questions. So to get from SO2 to SO3, we need to use this one. Cancel out the units. You end up with the one that you want. And 2 over 2 is just like saying 1 over 1. So if you start with 37.5 liters of sulfur dioxide, you make 37.5 liters of sulfur trioxide. How do we do for that one? Good. Here's one more. So I'm going to let you do it 100%. I'll give you 3 minutes to read it, write out your equation, and get to an answer. Alrighty, so hopefully you've had a chance to give this one a try. I like to highlight the things that are relevant in the problem. You know that. So we're looking at 15 liters of sulfur trioxide gas. We need to figure out how many liters of oxygen gas were required to make that. These are the two compounds involved. So we write out our ratios. We use liters instead of moles. Those are our ratios. Now we can set up the problem. We're trying to get 2 liters of oxygen gas. So that means we need to have liters of sulfur trioxide in the denominator. Make sure that your units cancel, and you're left with liters of oxygen gas. In your calculator, it's just 15 divided by 2. with sig figs at 7.50 liters of oxygen gas. Questions here? Let me know how you did. Okay. So that's all three problem types. Now we're going to add a concept on top of that, and it's the limiting reactant concept. So let's say you're making a grilled cheese sandwich. At the very least, you need 2 slices of cheese, 2 slices of bread to make one sandwich. We can represent that with an equation. 2 slices of cheese plus 2 slices of bread, you make one sandwich. So, let's say you're digging around in your kitchen and you're just gathering your ingredients. What do you have, right? Let's say you have 4 slices of cheese and 4 slices of bread. How many sandwiches could you make if you had 4 slices of cheese and 4 slices of bread? Yeah, you can make 2. What if I had 4 slices of cheese and 8 slices of bread? How many complete sandwiches can you make? Yeah, you can only make 2. Even though you have a lot of extra bread, you can't do anything with it because you don't have enough cheese. So you got 2 options. You go to the stove, or you stick it with 2 sandwiches and everybody else gonna get something else to eat. Silly concept to use grilled cheese sandwiches, but everybody gets it. If we were doing some kind of an experiment, right, we would call the cheese the limiting reactant. And that's because it's the cheese that's limiting how many sandwiches we make. And that means that the bread is in excess. We've got plenty of bread to go around. You can slap somebody high five with all the other bread that you have. Throw it at the wall. I wouldn't do that. That's wasteful. But you've got a lot of extra. So that reagent would be in excess. Let's apply that to chemistry. So with chemistry, we're still talking about ingredients, right? In a sense. And the limiting reactant is the one that controls the amount of product that you can make. It gets used up before everything else. Sometimes when you're in the lab, you've only got but so much of one of your reactants. And so that's just what you deal with. Maybe it's really expensive. Maybe it's hard to make. It could be any number of reasons why you have only a small amount of one thing and a ton of something else. Let's put this concept to use in a question. If you heat 5 moles of iron and 3 moles of sulfur, how many moles of iron 2 sulfide are formed? Let's break this down. We're being told about 2 of our reagents here, which reagent and reactant are the same thing. I have 5 moles of iron and 3 moles of sulfur. I'm combining these two to make iron 2 sulfide. Since I'm told about 2 of my reactants, that has to mean, and I'm asked about how much product I'm going to form, that's a limiting reagent question. So that's always going to be the case. You will be given 2 amounts. It could be moles, it could be grams, it could be anything. But you're given 2 amounts, and you need to figure out which one is the limiting reagent and how much of whatever product is formed. To do that, we have to answer 2 smaller questions. First question is, if I have 5 moles of iron, how much iron 2 sulfide will I make? The second question is, if I have 3 moles of sulfur, how much iron 2 sulfide will I make? We can answer these questions. We just have to use the mole ratio. For this one, we want to have moles of iron 2 sulfide on the top. You get that from the chemical equation. And there's 1. We need to have moles of iron on the bottom. There's 1. I have to rewrite this. It's just going to bother me. There. Our units cancel. We get the unit that we're after. So if we just had 5 moles of iron and all the sulfur in the world, we would make 5 moles of iron 2 sulfide. We have to do the same thing, only with the 3 moles of sulfur. We still want the iron 2 sulfide on top. And this time we're putting sulfur on the bottom. Once you do your 2 smaller problems, you have to answer a question. Which reactant makes the least product? So if you had to choose here, which reactant makes the smallest amount of product? Does the iron make the smallest amount or the sulfur? We're comparing these two. So that means sulfur. Sulfur makes the smallest amount of sulfur or iron 2 sulfide. So that is going to be our limiting reactant. And if that's the case, then we make 3 moles of iron 2 sulfide. That's the crux of the limiting reagent problem, is answering this question. Questions here? So of course, we're not going to stop there. We just learned 3 problem types that we can apply the limiting reactant concept to. Here's an example that I'm going to work through for you. But I want to ask your opinion. It's 9 o'clock right now. We have to finish up this part, and then we also have to talk about percent yield. Do you want to take a short break now, or do you want to finish class early? I know you always say keep going. I want to give everybody a chance. Okay. We'll keep going. Just want to give the option. I know sometimes people get tired, and I understand. So here's our example problem. How much molten iron is formed from the reaction of 25 grams of iron 2 oxide and 25 grams of aluminum? So, we're given 2 amounts. It's very likely going to be a limiting reactant problem. We've also got 25 grams of iron 2 oxide and we've got 25 grams of aluminum. We're trying to figure out how much iron we actually make. We've got mass to mass for both of these. So it's a mass to mass question with limiting reagent on top of it. So let's get to work. We've got 2 mini questions to ask, and I already wrote them out up here. If I have 25 grams of iron 2 oxide, how much iron will I make, the molten iron? And then my second question, 25 grams of aluminum, how much molten iron will I make? For the first question, I'm just going to write out the equation that we're going to use. So I'm not going to write out the plan, I'm just going to write out the equation. Here's where we're starting. I first have to figure out the number of moles. You'll have to calculate the molar mass here. But I've already got that done for you. Then we write our mole-mole ratio. What we're looking at with B over A, well, here's our A in this case, and our B. The B is going to be the amount of iron in the problem. You look at the chemical equation. Our A is the iron 2 oxide. Then we need the molar mass of iron to get from moles of iron to grams. And that is just from the periodic table. No calculations required there. Make sure that your units cancel. Now we have a mole ratio of 3 to 3, which is like saying 1. So when you're putting it into your calculator, if your mole ratio is equal to 1, you don't have to put it in there. If you want to, just to be in the practice of it, then you can go ahead and do so. So that's the first part. We figured out how much iron we would make if we had 25 grams of iron 2 oxide and all of the aluminum in the world. Now we've got to do the second part, which is if we had 25 grams of aluminum. We're going to go through the same process, but instead we're looking at the relationship between aluminum and iron. We get from grams to moles using molar mass. You look up aluminum on the periodic table. Then we have our mole-mole ratio. We're looking at B over A. Aluminum is our A. Iron is our B. The B is still the same. Our A is different. It's 2 moles of aluminum. When we do our calculation, we definitely need to put that in there. This last unit factor is the same as before because we're taking the moles of iron and converting to grams of iron. Make sure your units cancel. When you're writing this one into your calculator, use parentheses. Oops. That should be multiplied by. And when you put all of that into your calculator, you get 77.6 grams of iron. But we're not done. We did these two mass-to-mass problems, but we still haven't answered the question of how much molten iron will be formed if we mix 25 grams of iron 2 oxide with 25 grams of aluminum. We have to choose which reactant makes the least and go with that. So which reactant makes the least amount of product? Is it the iron 2 oxide or the aluminum? Yeah, so it's going to be that iron 2 oxide. So that means that we're going to make 19.4 grams of iron. And can't forget to do that last part at the end. You have to choose which one it is you're going to make. You're going to make the smaller amount. How do we feel about that one? Okay. And then I want you... Oh, I had another slide in here just in case I couldn't fit it all in there. But I managed to fit it all on one slide. I'm proud of myself. I usually run out of room. Okay. Now I want you guys to try it. I'll go through and help you set it up a little bit. And then you're on your own. How many liters of sulfur trioxide gas are produced from 18 liters of sulfur dioxide gas and 18 liters of oxygen gas? We're given two amounts, so that means it's going to be a limiting reactant problem. And we've got volumes. We're going 18 liters of oxygen, 18 liters of sulfur dioxide gas. How many liters, right? So this is a volume-to-volume stoichiometry problem with the limiting reactant concept on top of it. The two questions that you have to answer: you've got 18 liters of sulfur dioxide gas and 18 liters of oxygen. You need to do those two mini problems and figure out which one makes the least amount of product. That will tell you how much you actually make when you combine the two. I'll give you about 3 or so minutes, and then I'll check in and start writing out some work. So if you're not finished at that time, it's totally fine. You can keep working, and we'll get to an answer together. So let's get to it. We've got two of these volume-to-volume questions to complete, and then we figure out how much gas we'll actually make. The first question, we're looking at sulfur dioxide and sulfur trioxide. The B over A thing still works. Our A is the sulfur trioxide, and B is the sulfur trioxide. So you put B over A. This ratio is 1 to 1. So you would make 18 liters. For the second one, we're looking at oxygen gas and the sulfur trioxide. The A is the oxygen. The B is the SO3. SO3 goes on top. Oxygen goes on the bottom. Now that we've done our 2 mini problems, we have to answer the question, which reactant makes the least product? We're comparing 18 liters and 36 liters. We choose the smallest one. So that means SO2 is a limiting reactant, and we make 18 liters of sulfur trioxide gas. Questions about this one? How do we do? Volume to volume is like the ram in the bush. It is. Once you do the mass to mass and the mass to volume, you're like, okay, how much crazier can this get? And then you get volume to volume, and you're like, oh, this is easy. So hopefully you feel that way. Still do some practice, but volume to volume is pretty easy. Last concept, percent yield. In the real world, you never get the amount of a product that you actually think you're going to get. And what you actually make is called the actual yield. You get that from experiment. So you get to the end of whatever mechanism you're doing, you weigh your product, you get a certain number of grams, or you make a certain volume, what have you. What we've been doing is calculating the theoretical yield, and that comes from a limiting reactant problem. So you could have mass to mass, mass to volume, or a volume to volume question rolled into a percent yield question. So you may have to calculate the theoretical yield using one of those problem types. The percent yield is the amount of actual yield compared to the theoretical. and the equation is here. So it is a percentage. You take the actual yield, which you'll always be told. You can't figure that out any other way. You'll be told what the actual yield is. You divide that by the theoretical yield. You multiply by 100%. So real quick, I'll show you a sample problem. Suppose a student performs a reaction and obtains 0.875 grams of copper 2 carbonate. And the theoretical yield is 0.988 grams. You have to figure out what is the percent yield. This is going to be the easiest type of problem because you're given both values. The experimental or the actual yield, usually there's going to be something like obtains or some word like that that says this is what the person got when they did reaction. So our actual yield is 0.875 grams. Theoretical yield, we're told outright, 0.988 grams. The equation we use percent yield is the actual over the theoretical times 100%. So we put in the numbers that we just took from the problem. Actual yield, theoretical yield, when you do that math, you should get 88.6%. So now I have a question for you. Do you want to do a problem similar to this as practice? Or do you want to skip to the harder one where you have to do a stoichiometry problem first to calculate the theoretical yield and then figure out the percent yield? So a harder question, or do another one of these simple ones? Then here's your simple one. Same exact question, just changed it a little bit. I'll give you a couple of minutes to read it through and come up with an answer. Feel free to share your answer in the chat if you'd like. Otherwise, you can wait for me. Oh, sure, I can go back real quick. Why do we say real quick? It doesn't have to be quick. I think it's like trying to convince somebody, like, come on, man, just for a second. Like, that's all I need. You don't have to convince me. It's all right. I mean, don't make it 20 minutes, but it don't have to be real quick. It can be a minute or two. Alrighty. So I'm going to go ahead and throw it up on here real quick. See, I just said it real quick. Man, that is ingrained in the culture. All right. So our actual is 0.741 grams. Theoretical, 0.988 grams. Divide by one by the other. Multiply by 100%. You get 75%. So that is percent yield. That's how you calculate it. Now we're going to go and kind of combined all the things from chapter 9. So you combine 10.5 grams of iron 2 oxide with excess aluminum, and you make 6.25 grams of iron. What is the percent yield of the reaction? If you would like to work ahead of me, go for the gold. I ain't gonna hold you. If you're looking at this question like, wait, so it's too many numbers and I don't know what to do, then stick with me. Let's break down what we're being asked. So what has happened? You took 10.5 grams of iron 2 oxide and excess aluminum, and you made 6.25 grams of iron. So the question that we have is, we've got this much iron 2 oxide. How much iron should we make? This is our theoretical yield, which is missing from the problem. We're told another number, which is the 6.25. That's our actual yield. The first thing we have to do is figure out what our theoretical yield is. To do that, we've got to complete a mass-to-mass problem. We know what we started with, 10.5 grams of iron 2 oxide. We don't know how many grams we should end up with, and we need to calculate that. First step, convert those grams to moles. And just so you know, this is one of the reactions that we've done already. So you already have the molar masses for all the things if you had it in your notes. You don't have to calculate anything new for that. For our mole-mole ratio, our A is the iron 2 oxide, B is the iron. You look at the chemical equation, you've got 3. So we write that as 3 moles of iron, and another 3 moles of iron 2 oxide. Then we need to get from moles of iron to grams. We use molar mass to do that. Make sure all your units cancel properly. I've been doing this for a long time, and I still cancel my units to make sure that I set it up right. Sometimes you just write something wrong. You think one thing in your brain, you write it a different way. It could be something that simple that will get you the wrong answer. So make sure that you cancel your units and make sure everything lines up. When you're putting this into your calculator, that gets you the moles. 3 to 3, that ratio is 1 to 1, so we don't have to type that into the calculator. you should get 8.16 grams of iron. But remember, this is our theoretical yield. This is not the question that we're answering. We need to figure out what the percent yield is. Now we're ready to take our actual yield from the problem, 6.25 grams, divided by the theoretical yield that we calculated, 8.16 grams, and multiply by 100%. That's our final answer, 76.6%. So literally this one question takes into account almost every concept that we had. The only thing it didn't take into account was limiting reagents. And so I could throw that in there to say, okay, I've combined these two amounts of things. This is what I made. And you have to figure out what amount you make for your theoretical yield. And then do the percent yield calculation. But this is almost as complicated as it gets. So talk to me about this one. Do we think with some practice we could get here? Good. Then that's it for today. You've got Mastering Chemistry due on Sunday. So that's chapter 9. If you haven't started it yet, please do. Your final exam is going to be due Monday, May 3rd. It's a take-home. I will post it a week before it's due so that you can start working on it. It's going to cover chapters 9 and 10, kind of like an exam. So it'll focus mainly on that. But there will be some questions from all the other chapters that we've done. And you'll upload your responses just like you do with the chapter check-ins, only it's going to be the final exam. So it's not going to be on Blackboard. It's going to be like, the format is going to be like a chapter check-in. I'm going to upload a Word document and a PDF. You can print it out, you can type it up, whatever you want to do, but show me all your work. And then you upload that assignment, and that's your final exam. I grade that, and we're done. It'll be, the other thing is, yes, you will have a study guide. I always give you that. And it will be open note. So you can make a cheat sheet and you can use that. Or you can just use your notes. Some people find it more helpful to make like a sheet or a guide for themselves. But the final exam will be open note. No problem. The final exam is it's part of its own category. So it is a percentage of your grade that's outside of the regular exams. I can't remember off the top of my head what percentage it is. I want to say it's 20%. So it's a decent portion of your grade. If you have any other questions, feel free to ask. Otherwise, you're free to go.